First, I'd like to thank all of you for joining this session. Some of you even skipped lunch. I'd like to also thank my nominator, Ralph Jansen, and the selection committee for this prestigious award. And most of all, I'd like to acknowledge and thank the Ampaire team, whose innovation and accomplishments have made the compelling story for this content of the presentation. And they gave me the opportunity to share this fascinating story. As a woman, I'm very honored and proud to join the list of extraordinary men who's received this recognition before me. But I also like to point out another fact that Dimitri has left out in the introduction. Like several recipients before me, I'm a first-generation immigrant. As I think Dimitri is one too, and many of you here in the audience are, perhaps you're second, third, or fifth generation. And that is what really makes this country great. The immigrants are a powerful force in the American science and technology, contributing notably to innovation and entrepreneurship. Their contributions are essential for economic prosperity and for leadership in a globally competitive environment. I was fortunate to receive an excellent education in this country in my dream subject, aeronautics and astronautics. Luckily, I didn't get deported, but I can share that story with you some other time. And I have been able to pursue my career by working with the leading minds of our industry and witness the tremendous changes in the past 4 decades. In this presentation, let me share with you the story of the emergence of hybrid electric aircraft through the lens of the startup Ampaire. So Ampaire is this startup from Southern California, and started up by 3 brave young men, Kevin Nordiker, Corey Combs, and Brian Bilton. And their vision was to develop high-performance zero-emission aircraft. And the bottom, number 6 circle you see there is me. I was employee number 6, and I had been with the company for about 6 years, and I retired at the end of last year, though I'm still an advisor for the company. And I joined the company through knowing Corey, because years ago, while I was in Boeing, we tried to recruit Corey Combs. But fortunately, I was not successful. And years later, after my second retirement from Comac, I came back and was advised to talk to Corey, and he managed to convince me about the electric airplane. That's the future of aeronautics. So let's start from physics, the very basic total energy for flight. And many of you know this equation by heart. Just rearrange the lift, drag, and thrust and weight a little bit. And you get the range equation. And part of that is the total energy density, and the other part is the lift to drag ratio. And so let's take a look at the lift to drag ratio side. And so many of you are experts in airplane designs using really impressive aerodynamics methods, using the configurations, such as now we have the blended wing body, and also structures, such as the trusted brace wing. So that could give you a lot higher aspect ratio and slender wing to support the high L over D. And let's take a look at some of the examples of the L over D ratio in the history, all the way back from the Wright Flyer back in 1903. And you can see the lift to drag ratio has increased all the way from 8.3 to some of the recent transports, such as the 787, up to 22, 23, and with a blended wing body, even 25, 26, or perhaps a little bit higher. So we have progressed far, and in this case, you can see a simple 2x or 3x improvement from the very first day of powered flight. And how about on the range, on the total energy density side? On this side, our propulsion systems have also come pretty far, and all the way from the very piston engine to jet engines and so on. And even now we have the electric engines, right? And on the propellant side, we have flown the avgas and jet A's and so on. And now we have electrons from the batteries. And of course, on the materials and weight and volume improvement has drastically improved since the very beginning. But the metrics that we're using are a little different, not just the L over D, simply on the other side. And I'd like to share with you this report, and some of you might have seen this, which was a report that's published in 1941, and it was from this committee that's appointed by the Naval Academy of Science. And you can see the people that's in this committee are some very famous and very smart people, like von Karman or Millikan or Kettering. For example, Kettering was actually the director of R&D for General Motors back in the 20s and 30s. And he actually has 186 patents under his belt. And for example, all the cars electric starts, that was his invention, as well as the Freon, so that we can all sit comfortably in the car or using the refrigeration. And so this one says the gas turbine could hardly be considered a feasible application to airplanes, mainly because of the complexity with the stringent weight requirements. And so we all know that weight is in the airplane like a common currency in terms of talking about all the systems, right? And also at the bottom you see that it says if the current meaning 1940s internal combustion engine already has a weight of 1.1 pounds per horsepower. And in order to approach that figure, the combustion engine or the turbines would need to have something that is of that level and is beyond the realm of possibility of the existing materials. And let's keep that 1.1 number in mind. In fact, it translates to about 1.5 kilowatt per kilogram for the engines. So let's take a look at that for some of the common turboprops in this case. Excuse me, not turboprops. In this case, we have one. In fact, if you look at the figure on the right, which has one turboprop in there, that's the Cessna Caravan. And on the left, you have this plot, which is based on the airplane weight, kilowatt to weight. On the right is kilowatt to weight to the engine. So ironically, the turbine was the only one that actually is above the 1.5 kilowatt per kilogram. And on the very bottom, what you see is a lot of the general aviation airplanes, including the Wright Flyers. And on the right, you have the Cessna 172s and also my own airplane, DA-40. So, and I put in the solar impulse too, just for reference. So we haven't really gone very far, but if you divide out, for example, some of the ratios, is actually more than 10x to the Wright Flyers. Actually a lot more than what we have done from the L over D side. And of course, we just mentioned the propellant side, because we have progressed from avgas, though some of the general aviation airplanes are still burning avgas, to Jet A. And in the solar impulse side, it's actually using the electrons obtained from the solar panels. And so in this case, the power to weight ratio is not the only metric. In fact, more important, let's take a look at the fuel economics. In this table, what we have listed are some of the common turboprops. And you can see the fuel economics by two factors. One is two of those metrics. One is the passenger mile per gallon, the second to the last column to the right. And then the last column in terms of passenger liter per 100 kilometer. And so these are listed with the first flight in terms of the years and also the number of passengers. A general trend that we can see here is the improvement of the passenger mile per gallon, namely the passenger loading that is improving with the introduction of the higher loading. So all the way from the 9 passengers to 90 passengers, or excuse me, 78 passengers, you have such improvement. And all the way from 30-some mile per gallon to 68 or 90 passenger mile per gallon. So that's quite impressive. And if you put that in a plot, you can see that trend even more clearly. So on the left, you see the passenger mile per gallon, and you can basically fit a straight curve, a linear curve through all that. So definitely the 9-passenger one has a lower passenger mile per gallon versus the higher ones, such as ATR and such as the ATR aircraft. and some of the other ones. And all the way, it goes from 30-something to almost 100. And on the bottom, there's something for reference from the auto industry. So for example, the Toyota Prius could already get to 50 to 60 miles per gallon. And some of the electric vehicles using the equivalent miles per gallon, you can see 120 to 130 for the Teslas. And for some of the larger jets, you can see for 737-800, it's already like at 85 passenger mile per gallon, up to the MAX -8, which you can get over 100 mile per gallon, passenger mile per gallon. So that's all really great, but let's take a look at what if we have electric airplanes. And so in terms of the electric airplanes, we have to shrink the scale a little bit because the improvement is beyond the charts that you saw earlier. And so on the lower left, you will see this addition of a pipistrel. It's a pipistrel 4-seat that was in the 2011 NASA Green Challenge competition. And so it was the #1 aircraft for the efficiency. And so it was beyond the chart because the chart previous chart only went up to 100. And so this is up to 400 and something. So it's way out there instead of being down in the 30s and 40s. So it's like 10 times order of magnitude. And then on the right-hand side, you see also the liter per 100 kilometers metric. And so it's like way down. So instead of even higher than the 9-passenger one, it's way down there for, I think, 0.2 or something like that. So it's really dramatic, the improvement. And so what if we take the 9-passenger Cessna Caravan and make that electric? How's that going to work? And if we electrify that, how much would the passenger mile per gallon or the equivalent passenger mile per gallon be increased? And so what would you say is the answer here? It will be 0 because you're not going to get any passengers. Because just the battery alone for going 200 miles, and that's a reasonable assumption for a 200-mile range, using a 250 watt-hour per kilogram density, you're going to get a battery that is more than 2,000 pounds. And so try to put passenger in it and for a useful load is not doable. So let's go back to the physics and see what more we can do in terms of the integration, in terms of other new advantages that we could have. So going back to our favorite equation of the range, total energy density multiplied by lift to drag ratio, we could see that in the propulsion airframe integration side, there's a lot more you can do. For example, the distributed electric propulsion, I think several of you presented in this conference. And boundary layer ingestion, which is also termed BLI, and there's still a lot that's quite important that's not done for that technology. And also a lot of the winged eVTOLs use these integration techniques to improve the range. And of course, there are other aspects too to the integration, such as putting the battery or the propellant weight in the integrated structure. And so what Ampaire had done was also looking at some of these integration challenges, integration advantages. And so what you're seeing here is what we call the tailwind, and it's a brilliant design by Corey Combs. It has a really high lift to drag ratio. As you can see, it has a really high aspect ratio wing. And it uses the BLI, boundary layer ingestion, with a ducted fan in the back to really sucking the boundary layer and reducing the drag. And however, with all these new technologies on the new aircraft, a couple of things. First of all, to mature these new technologies take time, take resources. And similarly, and also to try to work this with a certification. For example, you're seeing this one, the BLI or the ducted fan is also acting as a flight control device. And so you have some integrated functional devices here too with the new technology. So the certification is going to be quite a bit of a challenge there. And so instead of looking at the new technologies for the integration, we go to the focus on energy optimized approach. So in our favorite equation here, we try to look for a practical solution that still yet produces a compelling fuel economics. And how do we do that? We do it through the real rapid iteration. So in this case, 3 key elements in here with our systems, the copper bird, the iron bird, and the flying test bed for the approach. And so with the energy optimized approach, let's take a look at the energy storage as a start. And so on this plot, what you're seeing is the weight versus the Caravan certified range. In this case, is including the 30 minutes reserve. And so you're seeing the 3 curves on the plot. But first of all, I'd like to point out the yellow straight line across, and that is the line for the useful load for the Caravan. And so any of the curve that goes above that means you need more weight in the useful load, so that's not going to make it. And then the 3 curves are namely for 185 watt-hour per kilogram and 300 and 500, so the progression of the battery density, energy density. So you can see that for the 500 watt-hour per kilogram density, you will have some room left for the rest of the passengers and other system components if you have. And so really without a clean sheet aircraft design for the 9-passenger aircraft, namely to improve the L over D or from the weight side, the practical compelling solution has to be a hybrid rather than an all-electric aircraft. And so let's take a look at the hybrid architecture that a good system engineer would do to start the trade study on this side. And so listed here are 4 different architectures. And so we have our series and we have our parallel architecture. In terms of the parallel, we have 3 different types, the integrated parallel, the independent parallel, and the series parallel. And so these are, and some of the schematics are shown here, and notice that these are only notional. If you go to some of the automotive website, you could see much more complicated design in here. So each one has some examples listed. So for example, for the series architecture, we have the Nissan e-Power. How many of you are driving the e-Power Nissan car? Oh, it's a pretty good series architecture. And in fact, if you look at the metrics that we're evaluating, such as the internal combustion engine's efficiency, the electric efficiency, and also the power setting for the internal combustion engine, which in case of all these architecture will be quite different. And of course, the option of having to do the ground charging, because some of the EVs are plug-in EV and some of the EVs are hybrid EVs, you actually do not even need to plug in, such as the Prius, one of the Prius models. And for us in aerospace, there's also the challenge of certification, developing the aircraft, and the time and cost that it will take, and also scalability. It's not just that we're making one airplane or designing one airplane, but actually you're trying to design one architecture that could scale to larger aircraft. And so that's in terms of simplicity, second to the last column, and also the emission. That's our ultimate goal, right, to try to reduce the emission. And so with all the study, you can see the summarized high, low, medium, and also optimized for each of those boxes. We ended up with an integrated parallel. In this case, it's similar to the ground vehicle Honda Civic. How many of you drive a Honda Civic hybrid? Wow, we're not really into oh, there's one. Yeah, it's a great car, and it's a really low cost for them to put together this architecture. And it's an optimized system, similarly with our Caravan, which we put in this optimized integrated parallel. And one of the key factors is our scalable, in terms of scalability, we need to have something that is this simple and is integrated parallel so that we could move on to other airplanes as well. And the option for the ground infrastructure, that's another very important one. In this chart, we'll summarize the energy optimization in terms of our flight mission, which is slightly different from the ground vehicles. And so a very simple mission here includes the takeoff, the climb, cruise, and descent. And also, this is a notional display of the use of the power. So for example, on the left side, you will see the fully rated electric power that's used for takeoff and even could be part of the cruise or even the whole thing if it's a real short trip. And then on the right side, we have the partially rated or part-rated electric power. So we term that FREP and PREP. And so in these combinations, we look for the optimization in terms of the size, weight, and power of the power plants that we put together. And in this case, you can see the three different types. These are both notional, and as you can imagine, when you put the complex system together, it could be a little bit variations here. And so the first one, which is fully rated electric power. So in this case, the takeoff and climb, you have the electric, and you could have very limited ICE or combustion engine for the cruise. And then the second one, which is the electric, only used for takeoff and climb. And the last one is a combination for both in terms of the takeoff and climb, which is the most critical, most demanding in terms of the power, in terms of the energy for our aviation use. And so considering the electric energy use, electric power use, and the combustion engine power, because we have to size the combustion engine, and the pros and cons in each, we finally chose the combined electric and combustion engine for the takeoff and climb part of the mission. One of the primary reasons is that the electric energy use in this case is really low or the lowest. And so what we end up doing is that we really have the peak shaving combustion engine for the better efficiency of that, and then also for the highest payload and range in this case. The only downside of that is that it will never really have a zero emission guaranteed, even though we could also use sustainable aviation fuel for the combustion engine side, and we have demonstrated that at the end of last year. And also the noise is not as low as if you were to do the fully rated electric power. And so we do a lot of simulations, including the hardware in the loop, the human in the loop simulations that's beyond the Copperbird and Ironbird. And this one is just a check on the actual physical control hardware and software for the thrust control and so on. And so I'm pretty sure lots of you have been very familiar with that. And another one very innovative side is that with a startup, there's not a lot of resources, but we use it very wisely. In this case, we bought an Ironbird frame from the boneyard. And so this is a Cessna 337 that we use. 337 has two engines, which is a push-pull. And so even if you exchange out one engine, they're in line, so the weight and balance and everything could easily be worked, and with a one engine failure, it's not like you have the typical twin engine. And also using this already made frame, we could check out the size fit and everything very quickly, so you don't need to waste time between the lab and the flight, and everything is already in place. And so here's the flying test bed with a 337 that's implemented with our system. So there are two versions of this. One version, Ampaire changed the rear engine like what's shown here. So it's changed to the electric propulsion units. And the other version, the front was changed. And depending on where the battery is at, then, because the battery really is a big impact on the weight and balance. And so you could do the rest of the design. And so once we did the flying test bed, we took it out on the road and did a lot of testing. So this next one is a flight test, a flight demonstration we have in Hawaii. And so it's got sound. And Kevin is the one that's narrator.
This program is a world's first. The chain of islands here in Hawaii offer a unique transportation challenge where travel is necessary for short distances. At Ampaire, one of the key words in our mission is being trusted, a trusted developer of practical, compelling electric planes. This program couldn't have been possible without Elemental Accelerator, Mokulele Airlines, and Southern Airways, who are actually shifting the structure of the industry from large planes down into these smaller regional planes. which ultimately are also more sustainable.
These test flights are really the culmination of hundreds and hundreds, not thousands and thousands, of hours that people have put in to make this happen. The hangars have been rewired, the new power supply is there, and we're ready to go.
Seeing Ampaire's role and how they can help communities is really inspiring.
And so we took it to Hawaii, and beyond that, we actually flew in other places with other supports of the different programs. For example, we went to the UK and flew in Scotland as well as England under the support of UKRI. And also during those flights, we have discovered that even without optimization, because here the control of the electric versus the combustion engine is purely done by the pilot, and even without any optimization, you could get 40% of improvement on the fuel cost savings. So that is really something to think, even without having any optimization. And then we also have our first flights in the following years. 2022, we have the Caravan, the hybrid Caravan's first flight, and followed on by another one of the 337 flying test bed that's sponsored by the APA-E. And then we also have, we also have the world's first commercial hybrid electric aircraft in terms of the mileage, total one charge mileage, and that is 1,375 miles. One charge. We flew basically from the Mojave Desert to Oshkosh with one charge. And the charge was done by a diesel truck. And then, so to date, there were 30,000 miles that's flown, and that is with 100% dispatch reliability. And then in terms of another milestone, a real important one, just a couple months ago, we have reached a major certification milestone with the FAA that's ahead of schedule, and receiving the approval from FAA for the G1 certification basis milestone is a significant reduction to the regulatory risk. And historically, those that have received this approval will go on and gain the full approval of the FAA for the certification. But ours, or Ampaire's, is actually the first hybrid electric system that's ever to achieve a G1 from FAA, setting the category defining precedent for the industry. And this chart, actually, we have some really exciting projects that will work together with the universities. Clockwise from the right top is the UC Berkeley experiment that we did that we successfully flew or test flight, the UC Berkeley flying capacitor multi-level DC-DC converter, and this was supported by ARPA-E Open 21. So in this experiment, we validated the operation of ultra-high efficiency converter at 800 volts DC. And this enabled the ability to have regulated high voltage supplies for equipment that requires it to optimize the system efficiency and in operation. And the second one, down the right, bottom right, perhaps some of you are in the audience, is from University of Illinois, Urbana-Champaign, and that is the ARPA-E funding as well. And so for the electric airplane, instead of using the pneumatic boots for them, the electro-thermal pulse de-icing capability was what we worked on. And so this is capable of efficiently and rapidly removal of ice from the aircraft wings. And then the one on the right-hand side is with the University of Arkansas, and that was done in 2023 as an ARPA-E circuit program. And in this program, we test a 250 kilowatt motor drive, and this is a Arkansas silicon carbide inverter. And so the flight test bed this flying testbed really gives Ampaire a rapid test tool for evaluating emerging technologies, and that's relevant for the flight environment. It is reconfigurable quickly, and so that we can rapidly introduce new technologies. And those successfully evaluated technologies will become part of Ampaire's product roadmap. How about that? You worked in universities, and right away you get into a product of the startups. And allowing this maturation of the TRL through demonstration from lab to flight. So this chart just shows some of the map of Hawaii in the UK and also the Alaska flight, showing that we're not just flying in the comfortable tropics, we're also flying in some really extreme weather conditions and up to Alaska. And then we also flew right around Camarillo to get the world record. And so this is a shot of the highly sleep-deprived team working in the beginning when we have the very first version of the hybrid electric system implementation on the powertrain on the Caravan. It took 15 months. And the second version, which was just done a few months ago so that we get to the conformal configuration for the FAA evaluation, that was done in 1.5 months or 1.5 months. So that's very impressive and very fast turnaround for the learning. And so how does that look on our previous chart of the fuel economy? As you can see, in this case, for the mile per gallon, we have the Eco Caravan that's just gone over the chart a little bit at 107. And also the liter per kilometer is also way down here. So this has been achieved with just the retrofit of the existing Caravan. And what's even more impressive is that if you take a look at the overall economics, including the operating costs. And so on the left-hand side, first of all, is the payload range. As those of you who are familiar in looking at this payload range curve, you'll see the blue one is the Eco Caravan one, and the yellow one is the original Caravan. And so we did cross at one point. The point is the 9-passenger, close to the 9-passenger with a 30-minute reserve point. And so we actually come a little bit short in terms of the beginning weight or the payload. But then beyond the 9-passenger, namely when you have 8 or less number of passengers, you actually get more range in this case. And then on the right-hand side, what you're seeing is the operating costs. In this case, in terms of the operating costs, we have cost per seat and cost for the trip. In each case, you can see some of the larger models, the Beechcraft and even the Twin Otter on the right-hand side, that the Eco Caravan, which is at the origin of this, performance much better. So you don't need to go to this large size in order to get the performance, such as with the passenger mile per gallon. But in this case, the operating costs, you always come out ahead as well. And next, Ampaire's hybrid electric system is scalable. And remember, this is one of our goals when we did all the system trait studies. And so the system architecture will allow the scaling up from the Part 23 airplanes, the 9-passenger, 19 passengers, and upwards to the larger aircraft to capture the turboprop market. And by partnering with the OEMs who build these aircraft, including the combustion engines, will allow the fast learning and the retrofitting and certification challenges. And this really helps accelerate the process to net zero goal in aviation. The designs also give us the opportunity to adapt to these emerging battery technologies so that we can upgrade the aircraft so that they will even become better with years. And ultimately, the vision is a new hybrid single-aisle Part 25 transport, as you see on the right there. The single aft engine and aircraft with the EPUs, or electric propulsion units, distributed across the wingspan, we believe will be the future. And let's see. This is close to the last chart now. So we find that this vision of the single-aisle hybrid electric aircraft is quite synergistic with that from our NASA colleagues. As you probably have seen the one on the right presented in another AIAA meeting a couple years ago. And both of these concepts have a single aft engine and multiple EPUs distributed across the wingspan. However, the systems, the devil's in the details, the system is something that could be slightly different, and that is really where we need to carefully study and optimize to get the best performance of the system as a whole. And this is the last chart. And so our NASA colleagues are really good at acronyms. In fact, the big dot on the right is the Susan electrofan. So the Susan stands for subsonic single aft engine electrofan. I like this name, as you can imagine why, but I like to propose that SUSAN stands for sustainable aft engine, single aft engine electrofan. In closing, when we seriously commit to the 2050 net zero emission goal for aviation, we must find a practical and compelling solution for the large transport, at least the single aisle aircraft, and due to the frequencies and everything, you know. If you look at this history of the most popular commercial jets through time, this was presented before, the trend shows that the development for the propulsion side actually reduced from 4 engines to 3 engines and then to the twins, with lots of improvement in the efficiencies and also in the reliability of the airplane. But so if you look at this, reducing to a single combustion engine is a natural next step in terms of both range and number of passengers. But this will be an evolution with the consideration of not just efficiency and reliability, but of the sustainability. So although it may be appealing to consider reduction to zero combustion engine with current energy storage and technology development pace, an all-electric aircraft will probably be limited only for short range for the or low-speed operation for the near future. So in summary, the hybrids help to bridge this gap, and it alleviates a couple of things. First, the challenge in new infrastructures, as especially the plugins, will require the new infrastructures. So this allows us to really build the infrastructure pragmatically, or introduce the new infrastructures pragmatically, such as the various airport constraints and everything. We need to look at those. And it also reduces demand on SAF, the sustainable aviation fuel, given that the supply currently really does not address the demand at the current pace or up to 2050. And we believe that this is the fastest way to reduce aviation emission at scale. So let's fly hybrid electric, and let's fly sustainably. And that concludes my talk. But finally, I'd like to thank a couple people. One is the CTO of Ampaire, Ed Lovelace, who's given me some really insightful and valuable critique of this package. And so is Martin Klump, the CTO of Saluki. And they both are just tremendous contributors to the development of the electric aircraft, a hybrid electric aircraft. Thank you. And I guess we're open for questions.
Thank you so much for this wonderful presentation. So I have a little coin to the new AIAA coins, and a medallion for you that reads the Wright Brothers Lecture in Aeronautics on one side, on the reverse side, presented to Susan Ying 2025. And I believe you are the first female to receive this award. Congratulations.
Wow, thank you, thank you. Thank you. Wow. Okay.
I'll take this one. And we're going to take questions right now, so we can please sit down.
All right.
Go from there. All right, so we have a few questions that have been coming in. So we'll start with the ones that they have the most votes. What challenges with the current airport infrastructure are you facing to support the aircraft?
It's a good question. In fact, that's one of the reasons why you want to start with a hybrid. So we're working with the various airports and with the various charging because, as you know, to operate the airport, you need certain level of megawatts of the electricity. So you don't want to brown out the airport. And so this has to be introduced methodically. And so first of all, of course, when we first introduced these airplanes, it's just 1 or 2 or 3. But when you have a whole fleet, then you need to do careful optimization. And also some of the airports are already having very powerful solar as well as wind, clean energy that's introduced at the airport or to the airport from the local grid. So it's really important because sustainable flights is actually a team sport, so we do want to work together with the infrastructure folks as well as with the people who are providing the charging services and so on.
The next question, what is the economic viability of replacing batteries at EOL, end of life?
So that's another really good question because with the batteries end of life, usually at the end of life for aviation, what we might want to do that is before it really reaches like the same stage as the electric car or automobile, for example. And so at the end of life, it is possible to have the batteries used for the second life for the ground facilities, such as storage at the airports. That will be a good one. And then beyond that, there's a whole recycle program similar to how the automotive batteries could do the recycle. But in aviation, we usually have a higher requirement. Yes.
Okay, the next one. What's the cost savings you envision for the passenger? Is it good enough to trigger price wars in airlines industry?
That is, I think, definitely the case because as we have seen that because of sustainability is really a big driver, particularly for some of these airlines. Now they have to demonstrate that they have the carbon reduction. And so for doing something like this, even though it could be just a small regional feeder to the large airlines, it will be good for them to use this as the credit for doing their the ticketing and so on for their larger airfare scheme. And I think we're going to see more and more airlines that are starting to really address this, not just from the buying the SAF as a carbon credit.
Compared to fuel cell hybrid systems, what benefits do your aircraft provide?
Comparing to the fuel cell, actually, we have done some studies with the fuel cell. In terms of the fuel cell, we felt that there will be introduction of more weight for the system. If you were to do the retrofit, the fuel cell itself, and also you might still need another battery, particularly for the high peak power. So in which case, unless you're really trying to go for a really long range, but in this case, I think we're talking about short to medium range. We think that the single battery hybrid still beats the fuel cell ones. And with the fuel cell, you also have to worry about hydrogen, and hydrogen is another thing because you have to worry about the green hydrogen and the distribution of hydrogen and everything and get it into the fuel cell. So we won't go there.
How long are the charge times currently? Also, how does charge time scale with the program?
So that's a good question. It depends on your battery technology. It also depends on your charging. For example, on the ground charging for the EVs now, just a couple months ago, you have this new technology in China. They could charge like a car with 600 kilometers that can charge in 10 minutes, something in that range. So the fast charging is not far away. Currently, with our experimental flights, we're doing like an hour's down for a couple hours flight. But that will improve very quickly.
What do you think is the possibility to achieve the hybrid aircraft commercially within a decade?
Well, Ampaire already sold quite a few airplanes to some of the small regionals. And I personally think that that's going to happen within the next couple of years. But first of all, we need to still get the certification over the hump here. And I believe the G1 milestone that we have accomplished really allows us to move fast now, because all we have to do is methodically work through the conformal configuration, the test, and the data, and work together with the FAA and EASA so that we could get it into the system in another couple of years.
Great. How would you address the need for much increased reliability of a single gas turbine aircraft for civil aviation use?
That's a really good question, because many of you, when you saw that tailwind, and I mentioned the certification challenge and so on, everybody's thinking single engine, forget about it, right? Well, actually, the Susan configuration is not really a single engine. It's like a 1.8 engine or something like that. In addition, the Ampaire's current Caravan is not really single engine, even though we're going to be certified as a single engine and uses the single engine operational constraints, but it's actually a 1.2 engine aircraft. So in the future, I personally think that the certification or the regulatory folks are probably going to have a different class of these quote-unquote single engine or a different hybrid architecture. Because you do have, it's not just the one engine's reliability, you have the multiple parts. You have the electric part, which is a lot more reliable. It could go for, like the Tesla goes for 1 million miles, right? And so I believe that's going to happen.
Are you actively working on larger passenger liner variants for your hybrid powertrain system?
We'd like to, but right now the focus is really on the certification and get that over, but then we need also funding for doing these large aircraft, and we really would like to do this in collaboration with not just the OEMs, with NASA and with universities as well. You saw all the technologies, because a lot of the innovation happened at the very ground level in the universities and the labs. So collaboration is really the key here.
With changes in the administration policies, how does your product apply to a non-sustainability perspective in a competitive market?
Well, market competition is one thing, and I think even though the administration, U.S. administration, is not really up for the clean energy vehicles, I think the market competition is going to drive this, not just the policy side. And I think because we're already very close, like within the next couple of years, I think we have an opportunity to make that. That's not to say that we didn't appreciate the funding from ARPA, from NASA, even from the Air Force to help us to get this far, because there's a lot of technologies, a lot of opportunities to use the funding to really drive to accelerate the progress of development.
Okay, the next one might be proprietary, but what is the current energy density per kilogram for your battery system?
Well, yeah, that is proprietary. But one thing I would like to add is that because I spend quite a bit of time in China and watching the improvement of that side of things. So in terms of batteries, I think it's without question, by the end of the decade, we will have at least 300 watt-hour per kilogram, or even semi-solid state to solid state type of battery development. But U.S. is not working fast enough. We need to. But battery is not just the one thing, but also the electric motors. So you know what's inside the electric motors, right? A lot of the magnets. And you know where the magnets come from. So I think we have a lot of things to do in the fundamental technology level and the manufacturing level to get this done.
Remind us, what is the Susan Electrofan acronym spell out?
Sustainable single aft engine electrofan.
You mentioned you were testing 800 volts. Are you planning to increase this to 1,000 plus volts?
Not immediately, but for this class of 9-passenger, that's what we're working with. And once you start doing the certification, you basically freeze your design. So that's what we're working at. For the future, yeah, that would be a possibility.
Have you been working on a network of recharging stations to be deployed at airports?
We're working with partners. We have several MOUs with existing partners to do that together with the airports.
Okay, So, very last question. Does Ampaire intend on being the leader in standardizing hybrid electric flight? What challenges do you foresee?
I think Ampaire is already a leader. It's a pioneer because it's the first one to get to the G1. And so I think the challenges is really just to commercialize this, working with our partners, customers. Any product without customers is not going to go very far, right? So I think when you have the customers adopting this in their fleets, then they're going to see the benefits, and then you will have more customers, you will have more adopters, and that is the plan.
Susan, thank you very much for your presentation and for all your leadership and the pioneering all these years. A round of applause for our recipient.